40 trillion kilometers away, in the cold darkness of the constellation Leo, there is a world that may be breathing. Not breathing oxygen like we do. There are no green forests, no oceans reflecting a blue sky. But if life exists there, it would exist in a completely different way, silent, distant, and beyond every earthbound imagination. Its name is K2-18b, about 120 light-years from us. K2-18b orbits a faint red dwarf star called K2-18. This star is smaller than the Sun, cooler, emitting a dim reddish glow, yet at just the right distance, a massive planet lies within the habitable zone, where temperatures could allow liquid water to exist. The problem is, K2-18b is not like Earth. It is about 2.6 times Earth's radius. Its mass is nearly 8 to 9 times greater. If a solid surface exists, then gravity there could be roughly twice as strong as ours. But what truly makes this world astonishing is not its size, it is its atmosphere. In 2019, the Hubble Space Telescope detected signs of water vapor in K2-18b's atmosphere. That alone was a shock. But everything escalated when the James Webb Space Telescope, the most powerful observatory ever built, turned its infrared eyes toward the planet. Webb did not only see water vapor, it detected methane, it detected carbon dioxide, and then a faint but haunting signal appeared in the spectral data: dimethyl sulfide, DMS. On Earth, DMS is produced almost exclusively by living organisms, especially marine microorganisms. Volcanoes do not generate large amounts of it. There are no common inorganic chemical reactions known to produce it in significant quantities. If DMS truly exists in K2-18b's atmosphere, then somewhere beneath those thick clouds, there could be life. Not cities, not forests, but an ocean, a global ocean. Scientists have begun calling this type of planet a Hycean world, a blend of hydrogen and ocean, a bold yet plausible idea. K2-18b may have a rocky core, above it a global ocean hundreds of kilometers deep, and above that a thick hydrogen-rich atmosphere. Not like Earth, not like Neptune, something in between. If that is true, it is not a cold, dead mini-Neptune. It is a vast ocean beneath a hydrogen sky. But nothing is simple. The red dwarf star, K2-18, emits bursts of ultraviolet and X-ray radiation. Stellar flares can erode the atmospheres of nearby planets. Many planets orbiting red dwarfs are tidally locked, one side permanently facing the star, the other locked in eternal night. If K2-18b is tidally locked, one hemisphere would be continuously heated while the other remains in perpetual darkness. That could create extreme atmospheric systems, possibly supersonic winds, and massive temperature contrasts. Yet newer models suggest that if the atmosphere is thick enough and rich in hydrogen, heat could be redistributed efficiently. The ocean might not boil away. It could even remain stable for billions of years. And here is the part that challenges our imagination. Hydrogen becomes a powerful greenhouse gas under high pressure. A dense hydrogen atmosphere can trap heat efficiently, allowing oceans to exist farther from a star than traditional habitable zone models predict. That dramatically expands the potential range for life in the universe. K2-18b does not orbit a sun-like star. It orbits a red dwarf, the most common type of star in our galaxy. If a planet around a red dwarf can maintain oceans beneath a hydrogen sky, then perhaps billions of similar worlds exist out there. But before we dream too far ahead, there is a major limitation. We have not seen the surface of K2-18b. Everything we know comes from light. When the planet passes in front of its star, a fraction of starlight filters through the planet's atmosphere before reaching our telescopes. Molecules in the atmosphere absorb specific wavelengths. From tiny dips in the spectrum, we infer chemical composition. That is how DMS was suggested. But the DMS signal so far is only a tentative hint, not a confirmed detection. Scientists remain cautious. The data must be observed repeatedly. It could be noise. It could be another compound with a similar spectral signature. Yet even if DMS turns out not to be present, the coexistence of methane and carbon dioxide in chemical disequilibrium is already intriguing. On Earth, methane and CO2 persisting together in significant amounts is often linked to biological processes, and K2-18b appears to have both. What makes this planet stand out is not a single molecule. It is the entire picture: its size, its location, its atmospheric composition, its potential for oceans, and its long-term stability. A world unlike Earth, but possibly wet. A world larger and heavier, with a dense hydrogen sky. An ocean hundreds of kilometers deep, perhaps warmed by a natural greenhouse effect. And somewhere in those depths, if microorganisms drift in the dark waters, they would never know that a civilization 120 light-years away is analyzing their starlight. We do not hear them. We see only shadows in a spectrum. K2-18b is not a confirmation of life, but it is the first exoplanet to present such a compelling combination of potential biosignatures. Observed by a telescope powerful enough to probe the atmosphere of a distant world in unprecedented detail. And if those signals are real, scientific history may be standing at the threshold of something extraordinary. A global ocean beneath a hydrogen sky. An ocean beyond Earth. A place where chemistry may have taken one more step. Beyond the boundary of the inorganic. K2-18b is not just a distant point of light, it is a possibility. And that possibility is enough to reshape the way we look at the night sky. If you could dive down onto K2-18b, you would not touch ground. You would fall. Fall through a sky that is neither blue nor black, but a vast ocean of dense, heavy, suffocating hydrogen gas. Light from the red dwarf star above would filter through thick haze, tinting everything a dim orange, like a permanent sunset. There would be no clear horizon, no land to stand on, only increasing pressure. K2-18b is not a scaled-up Earth. It may be an entirely different class of planet, something intermediate between a rocky world and a gas giant. Interior models suggest it could have an intensely compressed rocky and metallic core at its center. Surrounding that core may be a layer of supercritical material, where water is no longer water in the way we understand it. At pressures of tens of gigapascals and temperatures reaching thousands of degrees, water enters a strange state, behaving partly like a liquid, partly like a gas, partly like plasma. Above that layer, if the Hycean hypothesis is correct, lies a global ocean. Not a shallow sea like the Mediterranean, not an ocean 11 kilometers deep like the Pacific's deepest trenches, but perhaps hundreds of kilometers deep. An ocean without continents, without shores, without tectonic cycles like Earth's, just water, stretching from pole to pole. At such depths, the pressure would crush any complex organism we know. But microorganisms, anaerobic bacteria, life forms based on sulfur or methane chemistry, they do not require sunlight. They only require energy, and energy can come from many sources. K2-18b could possess strong geothermal activity if its core remains hot. Radioactive decay, gravitational contraction, or even tidal forces from its orbit could stir the planet's interior. Hydrothermal vents on the ocean floor, if they exist, might release hydrogen, methane, or ammonia. On Earth, life may have first emerged around such hydrothermal vents. If history repeats elsewhere, K2-18b is a candidate. But there is a paradox. A thick hydrogen atmosphere could generate a powerful greenhouse effect, preventing the ocean from freezing. Yet if it is too thick, it could drive surface temperatures to intolerable extremes. A planet within the habitable zone does not guarantee a habitable surface. Climate models for K2-18b vary widely. Some suggest surface temperatures could range between 0 and 40 degrees Celsius, relatively temperate. Others indicate surface pressures dozens of times greater than Earth's, with temperatures exceeding the stability limits of liquid water. It is even possible that the ocean exists only within a specific depth range, too cold above, too hot below. A habitable layer, squeezed between two hells. Meanwhile, the red dwarf K2-18 is not gentle. Stars of this type can live for tens of billions of years, far longer than the Sun, but in their youth they flare violently. X-rays and ultraviolet radiation can strip planetary atmospheres, break apart water molecules, and dry out surfaces. K2-18b orbits its star every 33 Earth days, close enough to receive the energy it needs, but also close enough to endure intense stellar radiation. If its atmosphere has survived billions of years of stellar flaring, it must be very thick enough to shield against radiation, and that is a double-edged sword. Dense hydrogen can block radiation, but it may also push surface pressure far beyond familiar biological limits. Any organism there would need to withstand pressures of hundreds of bars. Yet Earth has already shown that life can adapt to what once seemed impossible. Extremophiles survive at hydrothermal vents 4 kilometers beneath the sea, in acidic lakes, in granite rock kilometers underground. Bacteria have been found living inside nuclear reactors. Microorganisms have remained dormant for millions of years in permafrost. Life does not require ideal conditions. It requires stable conditions for long enough. And this is what makes K2-18b special. Red dwarfs live far longer than Sun-like stars. If K2-18b's orbit is stable, it could have tens of billions of years for chemistry to evolve into biology. Time is an immense resource. On Earth, life appeared relatively soon after the planet cooled. If that was not an exceedingly rare coincidence, then the universe may be filled with microorganisms. K2-18b could be the first hint of that possibility. But scientists are not declaring victory. There is a colder scenario. K2-18b may simply be a mini Neptune, with a gas envelope thousands of kilometers thick, beneath it a supercritical ice layer, and no true ocean accessible in a way that supports prebiotic chemistry. If the supercritical water layer is too deep and pressures too extreme, complex chemistry may be suppressed. An ocean does not automatically mean a living ocean. Current data cannot yet distinguish between these scenarios. James Webb has provided infrared spectra showing methane and CO2 coexisting. That suggests an atmosphere not dominated by ammonia or carbon monoxide, as seen on many mini-Neptunes. It hints at more balanced chemistry, but a few transits are not enough to build a complete picture. Each time the planet crosses its star, we collect only a tiny signal, blurred by stellar activity, instrument noise, and modeling uncertainties. Additional observations are planned. Scientists want more spectra at different wavelengths, more precise measurements of methane abundance, and confirmation or rejection of DMS. A single molecule definitively confirmed to have biological origin would change everything. But science does not run on hope. It runs on repeatable data. Meanwhile, K2-18b continues orbiting its star, one revolution every 33 days, 120 light-years away, close enough to observe, far too distant to reach with current technology. No probe could arrive there for thousands of years. Everything we know comes from light that left that planet long before the James Webb Space Telescope was even launched. We are looking into its past, and perhaps, in that past, an ocean moves beneath a hydrogen sky, where molecules collide, bond, and some form of chemistry repeats its first self-replicating cycle. If that happens, it will not be dramatic. No thunder, no flash of light, just a small reaction, repeating, until it becomes biology. K2-18b may be a cosmic laboratory where that process is unfolding. Or it may simply be a cold gas world with misleading chemical signals. Two opposing possibilities exist within the same dataset, and humanity stands at the boundary between them. Imagine that one day, the signal is confirmed, not a hint, not a probability, not a statistical fluctuation, but a clear, repeatable biosignature, one that cannot be explained by inorganic chemistry. At that moment, K2-18b would no longer be just another exoplanet. It would become a milestone. Humanity has experienced profound cognitive shocks before. When Copernicus removed Earth from the center of the universe, when Darwin showed that we were not created separate from nature, when early telescopes revealed that the faint clouds in the sky were actually distant galaxies. But discovering life beyond Earth would be an even deeper shift, not because we found aliens, but because we would realize we are not special. If K2-18b hosts biology, even just bacteria drifting in a hydrogen ocean, it would mean life is not a rare miracle. It is a natural outcome of chemistry under the right conditions. And if that is true on a world 120 light-years away, it may be true on billions of others. The Milky Way contains more than 100 billion stars. Most of them are red dwarfs. If even a small fraction host planets like K2-18b in zones capable of sustaining oceans, then the number of potentially life-bearing worlds is no longer in the hundreds. It is in the billions. A universe filled with oceans. A galaxy where water is not rare. And if microbial life is common, then complex evolution may simply be a matter of time. Yet even before biological confirmation, K2-18b has already forced scientists to rethink the definition of a habitable planet. For decades, the search for life focused on finding a second Earth, a rocky planet of similar size, orbiting a sun-like star, with surface liquid water and an Earth-like atmosphere. K2-18b does not fit that mold. It is larger, heavier, wrapped in a thick hydrogen atmosphere, and orbiting a red dwarf. If it can still support biology, then our old criteria were too narrow. That dramatically expands the scope of the search. Future telescopes are being designed with a clear goal: analyze the atmospheres of hundreds of similar exoplanets. Missions like LUVOIR or the Habitable Worlds Observatory aim not just to detect faint light, but to directly image distant worlds and separate their spectra in detail. The next generation of observatories may detect subtle chemical imbalances, track seasonal atmospheric changes, and even uncover signals we do not yet know how to look for. K2-18b may only be the beginning, but there is another dimension, less often discussed. If life exists there, it may be utterly unlike anything we know. No DNA, no familiar cells, no need for oxygen. Biology in a hydrogen ocean might be based on methane cycles. It could use sulfur or nitrogen in unfamiliar ways. It might function under pressures that would instantly denature Earth proteins. We search for biosignatures based on Earth's example, but perhaps we are thinking too narrowly. The universe has had 13.8 billion years to experiment. Earth is just one version. If K2-18b hosts life, it could represent a completely independent evolutionary branch, beginning with simple molecules and following a different path. Two biospheres, separated by 120 light-years, with no connection at all. That would mean life does not require Earth-specific conditions. It only requires opportunity, and opportunity may arise where we least expect it. But even if K2-18b ultimately proves lifeless, its impact will remain. It has changed how we build planetary climate models. It has forced us to develop more sophisticated spectral analysis techniques. It has reignited global interest in an ancient question: are we alone? That question is no longer purely philosophical. It is measurable. Each time K2-18b transits its star, scientists gather another fragment of data. Each fragment is a small step closer to an answer. And perhaps within the next decade, we will have enough evidence to tip the balance one way or the other. Perhaps we will discover another planet, even clearer, with an unmistakable chemical signature. Or perhaps we will confront the reality that complex life is extraordinarily rare. And Earth truly is an exception. Whatever the outcome, K2-18b has placed us at a remarkable moment in history. For the first time, we are not just discovering exoplanets. We are testing them for biology. From the faint light of a distant star, we are trying to read the story of an ocean we will never touch. Perhaps out there, beneath a dense hydrogen sky, chemical reactions are unfolding right now, as you watch this, on a world your ancestors never knew existed. Perhaps we are only one observation away from confirming that life is not exclusive to Earth. Or perhaps K2-18b will remind us that the universe is full of compelling illusions. But one thing is certain: we have entered an era in which the question of life beyond Earth is no longer science fiction. It is experimental science. And every new dataset from K2-18b pulls us closer to that boundary. If one day we receive clear confirmation of biology there, the night sky will never look the same. Every star will become a possibility. Every point of light will be an unanswered question. K2-18b is not just a planet. It is a reminder that we are living at a time when the universe is beginning to answer. And if you had to place a bet, what do you think lies beneath those hydrogen clouds? An empty ocean, or a distant, unknown biosphere? Leave your thoughts in the comments. Do you think K2-18b harbors life?